This lecture is a recap of whatever you have studied till now. In lectures 1 to 6, we first studied what is a force on charge, and afterwards we came with the formula which is W is equal to QV, where V is the potential difference between any 2 points. Let's say A and B. Let the potential difference at points A and B be represented by VA and VV. So, V is actually the potential difference between the 2 points. After that, we study thermal voltage and photoelectric effect. Thermal voltage is given to be equal to kT by Q. And as you can see that Boltzmann constant K and charge on an electron Q are constant. Therefore, thermal voltage varies only with temperature. After applying the values of K and Q, we will get thermal voltage to be equal to temperature in Kelvin divided by 11600. Similarly, if we apply T to be equal to 300 Kelvin, which is nothing but the room temperature, then we will get thermal voltage to be around 26 millivolt. You will be using this particular value of thermal voltage quite often. Photoelectric effect. In photoelectric effect, we studied that how a photon knocks out an electron for making its transition, and the maximum wavelength of the electromagnetic wave which can be used for performing photoelectric effect in Armstrong is equal to 12400 divided by bandgap energy of the semiconductor in electron volts. If you want to calculate the wavelength in micrometer, you will have formula 1.24 divided by bandgap energy in electron volt. We studied semiconductors and differentiated it with insulators and semiconductors. And in the later chapters, when we were discussing about non-degenerate semiconductors, we studied that if we dope an intrinsic semiconductor very heavily, then it behaves more like a metal. Also, at 0 Kelvin, semiconductors behaves more like insulators. And at normal temperature, say room temperature, the bandgap energy of insulator is of order 6 electron volt, whereas for semiconductors, the bandgap energy is of the order 1.5 electron volt. So it is much easier for a photon to knock out an electron in semiconductor for making its transition to conduction band. Therefore, its conductivity is far greater than insulators. Energy band theory of crystals is important for understanding how energy bands are created and why only one electron is allowed in a single energy band. The data in the form of a graph can be represented as this is energy and this is interatomic distance. When the atoms are far apart, they do not interact and act separately. However, when you bring them close, the outermost shells begin to interact with each other and finally an energy band is formed, so as to satisfy Pauli's exclusion principle, which states that every electron in an electronic structure should have different identity. And this particular portion is nothing but bandgap energy Eg. After that, we studied basic electricity theorems in which we discussed why Thevenin and Norton theorem are not applicable for majority of the semiconductor devices. However, mesh analysis and nodal analysis can be performed on the networks which contain semiconductor devices. After that, we studied what is the difference between intrinsic and extrinsic semiconductors, which was quite simple. If you dope an intrinsic semiconductor, then it will become extrinsic semiconductor. Intrinsic semiconductor is practically a pure semiconductor. However, The true definition of pure semiconductor also varies slightly from the intrinsic semiconductor, as if we have a semiconductor, then obviously it will have some boundaries, and at the boundary the construction of the semiconductor will change drastically. But the definition of pure semiconductor says that the periodic arrangement within the semiconductor should be regular up to infinity, which is obviously not possible. So, the pure semiconductor is a theoretical concept only. The word pure semiconductor and intrinsic semiconductor are used interchangeably. After that, we studied elemental and compound semiconductors. Elemental compounds like silicon, germanium, whereas compound semiconductors are like gallium arsenide, which is used in optical devices. We studied EK diagram, and the most important fact is the curvature of electron and hole in valence band and conduction band. You know the curvature will be narrower of electron in the conduction band because we studied in detail and derived the relation as well that the curvature is dependent upon effective mass. Narrower the parabola curve, the lesser will be the effective mass. And we also discussed that effective mass has to do nothing with the real physical mass. It is only a mathematical concept which are used only for calculation purpose for effective density of states and conductivity, etc. We have actually two types of effective mass. One was effective mass for density of states and the other was for conductance calculation. Further, both these effective mass have two different components. One is longitudinal effective mass and the other is transverse effective mass. These two different types of effective mass have separate formula. For density of states, the formula is where mc is the number of equivalent valleys in the conduction band. Similarly, we have net effective mass for hole in valence band to be equal to here mv represents the number of equivalent valleys in the valence band. You should keep in mind that the longitudinal effective mass for electron can be different than the longitudinal effective mass of hole. The same goes for transverse effective mass. Effective mass for conductance calculation, we have the formula asterisk sign is used for density of states, whereas kappa sign is used for conductance calculation effective mass. Whatever you have studied till now, like effective density of states, formula for different energy bands, you have used only the effective mass for density of states till now. You still have not studied any formula in which the effective mass for conductance calculations have to be used. So, by default, till now, whatever formula you have written, you have to keep in mind that we have taken effective mass for density of states in our formula. And afterwards, when we studied EK diagram and effective mass, then we discussed what are direct semiconductors and indirect semiconductors. For direct band semiconductors, the minima and maxima of conduction band and valence band in the EK diagram lies approximately on the same K value. However, in indirect semiconductors, the K value of maxima and minima of valence band and conduction band respectively does not lie on the same wave vector value. After that, we studied about Fermi-Dirac function, which is one of the most important topics which you have studied until now. Fermi-Dirac function in its original form is given as And we also studied Boltzmann approximation, which says that if E minus EF is several times greater than KT, then this one can be ignored and the formula can be written as. And we also studied Fermi energy level, which have two definitions. One is at 0 Kelvin, all the energy states below the Fermi energy level in a semiconductor will be occupied by electrons, and also at any random temperature, the probability of finding electron at Fermi energy level will be equal to 1 by 2. If we plot the Fermi-Dirac probability function, it will come out to be like this. This particular energy level where the probability is equal to 1 by 2 is the Fermi energy level. We found the formula for intrinsic Fermi energy level to be equal to EC plus EV divided by 2 plus 3 upon 4 kT natural logarithm of effective mass of hole divided by effective mass of electron. Remember that here also we have used effective mass for density of states. This formula can also be written as EC plus EV by 2 plus 1 by 2 kT natural logarithm NV divided by NC. And suppose if you have valence band energy EV and conduction band energy EC, then the Fermi energy level for an n-type semiconductor will obviously lie somewhere close to minima of conduction band energy. So the Fermi-Dirac probability function will be like this. Afterwards, we talked about density of states in the conduction band, which is actually a function of energy, whose formula is equal to. Similarly, the density of states per unit energy per unit volume in valence band is equal to. Here also we have to use the effective mass for density of states. Then we talked about effective density of states Nc and effective density of states Nv, and we also have derived the equation for Nc to be equal to. Similarly, Nv is equal to. If you remember the derivation, then you might recall that while deriving it, we initially assumed that the Boltzmann approximation is valid. So, these formulas for Nc and Nv are meant for typical non-degenerate semiconductors. When you will be studying the same concept in higher studies, then you will come to another formula for degenerate semiconductors also, which is very similar to this formula. However, it is only similar but not the same. After that, we studied the intrinsic carrier concentration, which is equal to Nv into Nc exponential of minus bandgap energy divided by 2 kT. We also have the formula for bandgap energy, which is equal to 1.21 minus 3.6 into 10 to the power minus 4 multiplied by temperature in Kelvin, and this particular equation for bandgap energy is for silicon. Similarly, we have bandgap energy equal to 0.785 minus 2.23 into 10 to the power minus 4 multiplied by temperature in Kelvin, and this particular equation is meant for germanium. In some books, you will find the formula for intrinsic carrier concentration Ni2V of the form A naught multiplied by T raised to the power 3 by 2 multiplied by exponential of minus Eg divided by 2kT. And in the detailed lectures, we have also found the value of A naught by putting the value of Nc and Nv into the intrinsic carrier concentration. And also, we found that A naught is actually dependent upon effective mass. And here, by this formula, you can find the Fermi energy position for intrinsic semiconductors. However, for finding the Fermi energy position for N-type or P-type semiconductor, we initially assumed that the semiconductor has been doped such that the doping concentration is significantly greater than intrinsic carrier concentration. Also, after assuming that the doping concentration is significantly greater than the intrinsic carrier concentration, we come up with the formulas, which is free electron concentration to be equal to intrinsic carrier concentration multiplied by exponential EF minus EFI divided by KT. We also derived another formula for free electron concentration to be equal to Nc multiplied by exponential Ec minus Ef divided by Kt. We have derived both the formulas, however, there is no need to actually learn both these formulas because this particular formula has been derived from this formula, as Ni itself is equal to Nc multiplied by exponential Ec minus EFI divided by Kt. After simply rearranging this term into a way such that you can put the value of Ni in this equation, then you will get this formula only. We already discussed the Fermi energy position for intrinsic semiconductor, which was similarly, we also derived the formula for Fermi energy level in N-type semiconductor to be equal to where Nd is a doping concentration of donor impurity. When the donor impurity is significantly greater than intrinsic carrier concentration, then the free electron concentration in the semiconductor is nearly equal to Nd. So you studied the modified formula, but the exact formula for Fermi energy level in N-type non-degenerate semiconductor is. Similar analysis can be done for P-type semiconductor. The formula is very similar, only there is a change in the sign of Kt term. Here, Na represents the concentration of acceptor impurities. All these formulas are very important and you have to learn them. Both formulas as well as the derivations should be crystal clear to you. And at the last, we talked about degenerate and non-degenerate semiconductors and discussed that this is the region where if the Fermi level lies, you cannot say for sure that this type of semiconductor is either degenerate or non-degenerate. However, if the Fermi energy lies between this region, then it will be non-degenerate and here it will be degenerate. We have discussed few properties of degenerate and non-degenerate semiconductors, and we have also discussed that for both types of semiconductors, the Fermi dipolarization function is valid as well as the standard definition of effective density of states is also valid. At least you can say that if you are going to use the Fermi dipolarization function for finding the polarity of an energy band within 3 kT of Fermi energy level, then you have to use the original Fermi dipolarization polarity function and you cannot apply the Boltzmann approximation. For non-degenerate semiconductors, we can say that EC minus EF will be significantly greater than 3 kT if it is an n-type semiconductor. Similarly, EF minus EV will be significantly greater than 3 kT if it is p-type semiconductor. However, if it is said that it is a degenerate semiconductor, then you cannot say for sure where the Fermi energy level will be lying. After that, we studied bandgap mirroring effect, in which we discussed how when the doping concentration is too high such that the dopant atoms also comes very close, resulting in an energy band of donor energy level also, making the net effective energy band gap of the semiconductor to be smaller than the original value. Bandgap mirroring effect occurs in heavily doped semiconductors, or in other words, degenerate semiconductors. The word degenerate comes from the fact that the discrete donor energy level degenerates into an energy band. After that, we studied degeneracy factor and discussed how the spin up and spin down factor introduces a degeneracy factor which changes the concentration of electrons present at donor energy level. And also, degeneracy factor G is not the same for n-type and p-type doped semiconductors. For n-type, the value for G is equal to 2 for silicon and gallium arsenide. However, for p-type, the value is equal to 4 for silicon and gallium arsenide. After that, we discussed the freeze-out region and also derived the formula to find the value of relative number of electrons which are present at the donor energy level with respect to total number of electrons which are present in donor energy level and in the conduction band. And the formula comes out to be like this. In the group's description, I have attached my notes. So if you want to take help, you can download them and can write notes taking help from it. After this, you will be having a few sets of questions, and I will advise you to solve at least one book so that you will be having some practice. Because the questions which you will be solving here are time based. So basically it is a type of a test. Also, there are few questions which are designed by me only. So not only the questions, you check the solutions as well. And if you find any mistake or error, then please let me know